All right, back again for another deep dive.
It sounds good.
This time, we're diving into, well, you wanted us to explore the physics of a block sliding on an incline plane.
Right.
And you know what's really cool about this? You sent us this awesome material about an interactive simulation,
Yes.
and it uses your phone's accelerometer.
Yeah, pretty neat.
Like, how cool is that? So we're not just going to be, stuck with numbers and formulas.
Nope.
We're going to actually be able to see these forces, like gravity and friction,
Right.
playing out, like, right in front of us.
Exactly. It's like it takes this concept, might seem kind of a bit dry
Yeah.
when it's just on paper, like here's a block, here's an incline, some arrows.
Right.
But this simulation, it makes it like a real experience.
Totally.
It's called block sliding on an incline plane.
Catchy.
It's a JavaScript model,
Okay.
which is great because you can run it pretty much anywhere.
So, like, on my phone, on my computer?
Yep, any web browser. But the really cool part is that it uses your phone's accelerometer
Right.
to actually control the angle of the incline.
Whoa.
Yeah. So you can, like, tilt your phone and you're changing the experiment.
That's amazing. So I don't even need, like, a fancy lab setup or anything.
Not at all. And if you're on a computer, there's a no sensor mode.
Okay, that's good to know. So I'm trying to picture this in my head.
Yeah.
What would I actually be seeing on the screen?
Okay, so you'll see the block, right? Sitting there on the incline plane.
Got it.
And right next to it, you'll have this force body diagram.
Force body diagram. So that's basically showing all the forces acting on the block, right?
Yeah, exactly. Like a visual breakdown. You've got the normal force
Okay.
pushing up from the plane, gravitational force pulling it straight down,
Uh-huh.
and then, of course, you've got friction working against the motion.
Right, of course. Trying to slow things down.
Exactly. But the cool part is these forces, they're not just like static arrows.
I see.
They actually change.
So they, like, grow and shrink.
Yeah. And even change direction as you mess around with the simulation.
Okay, so it's not just like a watch and learn kind of thing.
No, not at all. You can interact with it.
Okay, now we're talking. What can we actually do with this simulation?
Oh, lots of things. You can change the block's starting position.
Mm-hmm.
You can give it a starting velocity.
Okay, so, like, I can give it a little push.
Exactly. And then even play around with the coefficients of static and kinetic friction.
Wait, hold on. Back up a second.
Sure.
Remind me, what are those coefficients all about again?
Right. Good point. So basically, they describe how much friction there is between the block and the incline.
Okay.
Think about, like, sliding a block on smooth ice versus on, like, rough concrete.
Yeah, big difference.
Right. That's what the coefficients represent. The higher the coefficient, the more friction you get.
Got it.
And in the simulation, you can actually adjust these values and see how it affects the way the block moves. Of course, it has a few limitations. Like, the maximum static coefficient of friction is capped at 5.
5. Wow. That's like super sticky sandpaper or something.
Pretty much. It lets you explore those extreme scenarios, the ones you wouldn't normally see in real life. Now, the material you sent over also includes a set of physics exercises to help you really understand what's going on.
Like taking the simulation to the next level.
Yeah. It's like, okay, now you can use this simulation to actually solve some problems.
I love a good challenge. So what kind of brain-bending puzzles are we talking about here?
Well, let's start with exercise 3.
Okay.
It says, the formula for the force of friction, F, when the block is not slipping, is F exhaust force N, where N is the magnitude of the normal force.
Okay, got it.
But the simulation shows that the force of friction changes as the surface tilts.
Okay.
Explain why the force of friction is not constant.
Wait a minute, that's kind of tripping me up a little.
Yeah.
I always thought friction was just about the surfaces rubbing together.
Yep.
Shouldn't it stay the same no matter how steep the incline is? I mean, it's still the same surfaces, right?
That's a common thought.
Yeah.
What's important here is that the normal force,
Okay.
which is the force the surface exerts on the block,
Right.
that changes as the incline tilts.
Oh, okay.
Imagine holding, like, a book against a wall.
Uh-huh.
That force you're applying, that's the normal force. Now, if you start tilting that wall,
Right.
you have to push less and less.
Yeah, to keep it from falling.
Exactly. And the same thing is happening with the block on the incline.
Oh, so it's like the incline is helping to support the weight of the block.
Exactly.
So there's less force actually pressing it against the surface.
Precisely.
Okay.
And because the force of friction depends on that normal force, remember the formula,
Right.
it changes too. The steeper the incline,
Uh-huh.
the smaller that normal force, the weaker that force of friction.
Ah, so it's all connected. The angle of the incline, the normal force, the friction, it all works together.
Right.
I'm starting to see how this simulation can really help you visualize all of this.
That's the power of interactive learning. You can actually see those forces changing as you tilt the incline instead of just looking at a static diagram.
Absolutely. Okay, so we've tackled the mystery of why friction isn't constant.
Right.
What other aha moments can we uncover with these exercises?
Well, exercise 4 dives into the relationship between static and kinetic friction.
Okay.
Static being the force that keeps the block from moving initially, and kinetic friction being the one that acts once it's already sliding.
Okay, got it.
This exercise really challenges you to think about, like, what happens when the static coefficient is actually less than the kinetic coefficient?
Hold on. So that means it's easier to keep the block moving than it is to get it started in the first place?
You think so? Right.
That seems kind of backwards.
Yeah, it seems counterintuitive. But the simulation lets you test these, like, seemingly impossible scenarios and see what actually happens. It forces you to confront those assumptions and really dig into the physics.
I am definitely intrigued. I'm seeing how this simulation can really push us to think critically about these concepts.
Exactly. And the exercises, they keep getting more challenging.
Okay.
For example, exercise 5 asks you to calculate the maximum angle
Okay.
the incline can reach before the block starts to slip.
I see.
So you can play around with different static coefficient values and then actually test it out
Oh, that's cool.
by observing the block, seeing how it behaves in the simulation.
So it's like putting our physics knowledge to the test.
Exactly. We're not just messing around with a virtual block.
Yeah.
We're solving real physics problems.
I like it. Tell me more about what these exercises have in store.
Well, exercises 6 through 9, they get into, really trying to predict how the block will move
Okay.
under different conditions, different angles, different speeds, friction, all of that.
So we have to take all of that into account.
You got it. And then try to figure out things like how far it's going to travel before it stops, or like if it's going to hit that bumper at the end.
Oh, interesting. So like it becomes a detective story almost.
Yeah, exactly.
Gather all the clues, analyze the forces,
Right.
and then try to predict what's going to happen. I'm ready for the challenge.
Yeah.
But before we jump into those,
Yeah.
I'm curious. We talked about, friction changing as the incline tilts.
Right.
But what about different surfaces?
Ah, that's a great question. And it really highlights a key point here. This simulation, while really useful, it is a simplified model.
Okay.
It focuses on these fundamental principles of inclined plane physics.
Right.
But it doesn't capture all the nuances of, like, real-world scenarios.
So the friction coefficients we've been talking about,
Yeah.
they represent like an ideal situation.
Exactly. In the real world, friction's way more complex than that.
Oh, yeah, for sure.
The type of surface, whether it's ice, concrete, wood, sandpaper, the texture, the temperature, even the humidity, all those things can affect the amount of friction.
Okay, so to make the simulation even more realistic,
Yes.
we need to introduce different friction coefficients for all these different materials.
Exactly. You could even take it further and add things like surface roughness,
Oh?
or like if there's any lubricants. Imagine being able to test out how a block slides on a surface coated in oil.
Whoa, okay. You're blowing my mind a little bit.
Yeah.
But I love it.
Yeah.
It's like we're taking this deep dive to a whole new level of complexity.
Exactly. We can start with a simple model
Right.
to understand the basic principles.
Yeah.
And then keep adding layers to make it more and more realistic. But for now,
Yeah.
let's stick with our idealized model
Okay.
and tackle those physics exercises. Ready to dive into exercise 6?
Absolutely. Bring on the challenge.
All right.
All right, so exercise 6, let's do it. Feeling like a physics detective here, ready to solve this case. What's the scenario?
So exercise 6, it gives us kind of a simple situation to start with.
Okay.
The incline is flat.
Okay.
So the angle of inclination, theta, is 0 degrees.
Got it.
The block is given an initial speed of 3 meters per second to the right.
All right.
And the challenge is to figure out, okay, how far is that block going to move before it stops?
Wait, hold on. If the incline is flat, shouldn't it just keep going forever? Like Newton's first law of motion. Right. An object in motion stays in motion.
Right, but that's where those friction coefficients come in.
Ah, right.
Even though there's no incline for it to, fight against.
Yeah.
Remember those values we talked about? The static and kinetic friction?
Mm-hmm.
So the exercise, it specifies that the static coefficient of friction is 0.5.
Okay.
And the kinetic coefficient is 0.4.
Got it.
So that friction from the surface, it's going to act like a brake.
Right.
And eventually bring that block to a halt.
Okay. Makes sense.
And to solve this, to crack this case, we got to put on our physics hats here.
All right, let's do it.
Think about kinetic friction and work. Work, in physics, it's the force applied over a distance.
Right.
So in this scenario, the work done by friction, that's what brings the block's kinetic energy, its energy of motion, down to zero.
I'm seeing how these exercises, it's not just about plugging numbers into a formula.
No, not at all.
You really have to think about these concepts, how they all work together.
Right, and the simulation, it allows us to actually visualize this.
Cool.
You can set that initial speed, you can play around with the friction, and watch as it slides to a stop.
Mm-hmm.
It's really great for developing an intuition for how these different factors, how they all interact.
Totally. Okay, so we solved the flat incline mystery. What happens when we start tilting things up again?
That's where things get a little more fun.
Okay.
Exercise 7 takes us to an incline of negative 30 degrees.
Negative 30.
Yeah, so that means it's sloping downwards from left to right.
Oh, okay, got it.
The block starts from rest at the top of this incline.
Okay.
And it's given an initial speed of 3 meters per second up the incline.
Oh, so now it's battling gravity and friction. It's like trying to run up a down escalator.
I love that. That's a perfect analogy.
Right.
So the exercise wants us to figure out how far is that block going to travel up the incline before it stops and starts sliding back down.
I can almost see it in my head. This feels like, a classic physics problem.
Yeah.
Drawing all those force vectors, breaking everything down into components.
Exactly. So this exercise, it really makes us think about forces acting parallel and perpendicular to the incline.
Okay.
That component of gravity acting parallel to the incline, that wants to pull it downwards.
Right.
Working against its upward motion. And then friction, it adds another layer of resistance.
So it's like a three-way tug of war. The block's initial speed, gravity, and friction. And we got to figure out which one wins out and by how much.
You got it. And again, with the simulation, you can actually visualize this whole struggle. See how its velocity changes as it moves up?
Oh, wow.
It gradually slows down until eventually it reverses direction. It starts sliding back down.
That's so cool. Okay, so we've seen a flat incline, a downward slope.
Right.
What's next? I bet exercise 8 throws us an uphill climb.
You know it. Exercise 8 sets the incline angle to plus 30 degrees. So now it slopes upwards from left to right.
Okay.
This time the block starts from rest at the bottom.
Okay.
And it's given an initial speed of 1 meter per second up the incline.
So it was kind of like the previous one, but reversed.
Yeah, exactly.
Trying to see how far it goes up before gravity and friction pull it back down.
There's a twist this time. It doesn't just ask how far it travels up.
Okay.
It wants to know, will the block stop before it reaches the end bumper of the simulation?
Ooh, that adds another layer to it.
Yeah.
I'm guessing that depends on the friction, right?
You got it. The exercise tells us the static coefficient is 0.6.
Okay.
And the kinetic is 0.4.
Right.
So we got to use these values to figure out, is the friction strong enough to bring that block to a halt before it crashes into that bumper?
It feels like we're really putting all the pieces together here.
Exactly. And if the block does reach that bumper, we also have to figure out its speed at that point. So we're thinking about distance, speed, whether it stops or hits the bumper. It's a full-on investigation.
This is amazing. I'm really seeing how this simulation helps you understand these concepts in a way that like a textbook just can't.
Totally. And there's one more challenge in exercise 8.
Oh, there's more?
Yeah. It asks, what kinetic coefficient of friction would be needed for the block to move at a constant speed down the incline?
Constant speed. So that means all the forces are balanced, right? It's like when you're walking down an escalator at the same speed, it feels like you're standing still.
Exactly. That's what we call dynamic equilibrium in physics.
Okay.
So if that block is moving at a constant speed, that means the force of gravity pulling it down, that's perfectly balanced by the force of friction acting in the opposite direction.
So we need to find that sweet spot where the friction is just right to counteract gravity's pull. I'm seeing how this could be useful for designing things like ramps or conveyor belts.
Exactly. Understanding how gravity and friction play together on an incline, it's really important for engineering and design.
Totally. Okay, we covered so much with exercise 8 alone. What does exercise 9 have in store for us? All right, hit me with exercise 9. What's the final challenge in our incline plane adventure?
So exercise 9, it takes us back to a familiar setup.
Okay.
We've got that plus 30-degree incline.
Right.
Block starts from rest at the bottom.
Mm-hmm.
Initial speed of 1 meter per second up the incline.
Okay, I remember this, but there's a twist, right?
Of course. This time,
Yeah.
we got to figure out what kinetic coefficient of friction
Okay.
would be needed to make the block stop sliding right before it hits that bumper.
Oh, interesting. So it's like we're working backwards this time.
Exactly. We know what we want to happen.
The block comes to a nice, smooth stop.
Right before the bumper.
Yeah.
And we got to find the friction that makes that happen.
It's like a reverse engineering problem.
Exactly. It really tests our understanding of, how force, motion, and friction all work together on that incline.
It feels like we're bringing everything together.
It is.
We started with a flat surface.
Yeah.
Then went to uphill climbs.
Right.
Now we're fine-tuning the friction to make the block do what we want.
That's a great way to put it. And, even though we've been focusing on, a simplified model, these exercises, they give us a taste of how physicists, how engineers use these concepts in real life.
Absolutely. I mean, we've talked about ramps, conveyor belts.
Right.
But I bet there are tons of other examples out there.
Oh, yeah, for sure. Think about designing roads on hills. Understanding how friction changes with the incline is so important for safety.
Right. Or even something like a playground slide.
Exactly. The angle of the slide, the material it's made of, that determines how fast you go, how smoothly you stop.
You're right. Incline planes are everywhere.
Yeah.
I'm never going to look at a ramp or a hill the same way again.
I know, right? And that's the beauty of physics. It helps us see the world differently, to understand the forces all around us.
Well said. I got to say, this has been a fantastic deep dive.
I agree.
We explored the simulation, tackled those challenging exercises,
Absolutely.
and even uncovered some real-world applications. I feel like my physics knowledge has leveled up.
It's been awesome exploring these concepts with you. And remember, curiosity, that's the key to unlocking the universe.
Couldn't have said it better myself. And to our listeners, we encourage you to check out the source material. Maybe even play around with the simulation yourselves. It's a fun and interactive way to learn about this fascinating world of physics. Keep those brains sliding.
And remember, physics isn't just about equations and formulas. It's about understanding the world around us.